Okay, so hi everyone. Um, let's just double check. Yes, audio setting. All right, so hi everyone and welcome to lecture 14 of ECE 3311, Principles of Communication Systems. So in today's lecture, what we're going to be talking about in particular is we're going to follow up what we initially talked about with passband communications and the magnitude phase and in-phase and quadrature representations of the passband signals, okay? And then we're going to look at the different types of receiver structures that, transmitter structures that create, at least the theoretical transmitter structures that create these waveforms, okay, at the passband. And then, very importantly, we're going to be talking about the super heterodyne receiver, okay? And that's kind of a fun topic in order to, with respect to creating a receiver front end that takes a passband signal and then progressively brings it down to baseband. All right. Okay. So let's get started. So here we go. There we go. So what we saw last time, first of all, yeah, we're golden. So I just want to make sure we're okay. Let me go back to full screen. So what we saw last time, or the first lecture when we talked about passband communications, is that equation 1 represents a modulated signal to passband, all right? It consists of this guy here, the G of T. Okay, and it's a mapping to a baseband representation, and could be a complex representation too, from a message signal M of T, right? And that could be analog or it could be digital. And then we modulate it to a carrier frequency omega T. So, or it could also be 2 pi FC of T, right? Depending on what you want it to be, you know, if, F or omega, whatever your representation of frequency is. Then, from there, we have like either one of these two representations here. So let's actually go into writing what these are, all right? So again, so let's just recap. Okay, so passband signal, PB, is equal to the real operator of the mapping of an information signal, M of T, to a baseband signal, BB, e to the j 2 pi fc of t. Again, this could be represented as omega c too. All right. And we are told that this fella here can either have one of two representations. Okay. So this G of M of T, okay, can either assume the form X of T plus J Y of T, right? And this here, we call it the in-phase quadrature representation, I and Q, where, let's use highlighting. This here is the in-phase component, and this here is the quadrature component. So in-phase, and that's the quadrature. Okay, now we also have another way of representing this, which is G of M of T, okay, can be equal to R of T e to the omega T, okay? And in this case, okay, we have these two, okay? We have the magnitude, and we have the phase, okay? Now, this here, what we refer to this, okay, is the magnitude phase representation. Okay? So what we've got, okay, are these two ways of representing our complex, okay, because this could potentially be complex. So this baseband representation, okay, could be complex. Okay, that's the number for that's the symbol for complex. Now, there is a relationship between the two, right? So R of t, okay, can be equal to the magnitude, the square root of xt squared, okay? And the phase can be represented by the arctan of y of t over x of t, okay? So we could have, that's one way of mapping, right? Okay, so that's kind of the relationship that these folks have with each other, okay? And then the other way, of course, is you know, if you want to represent what this thing is, you know, the reverse is that you take you know, the real and imaginary parts of the expression for r e to the j omega t. Okay. Now, this is great. Okay, we've seen this before, but now, how does this get implemented in a communication system, right? So let's look at this thing first. Oh, and you might say, okay, what the heck is this? Where did we get this? Well, let's work this out mathematically, right? So if I were to let's say we do the g of m of t. Okay, we start off with this. E to the j 2 pi fc of t. Okay, so let's say we first do the IQ approach. So we replace the mapping. Okay. All right. Euler. Okay. And what Euler will do is the following. We're going to have mu mu okay, and we work this out. Okay, so we multiply this with this, this with this, this with this, this with this. So we should have 4 terms. Up. Yeah, correct. Yep. And then yep, because it's j times j, so it's -1. Okay, now the real operator means that we only extract out real components, which are this and this. So these get ignored and are not carried forward by the real operator. So at the end of the day, we get this representation. Ah, slight error. Okay, so that is one way. So if we take the in-phase quadrature representation, what we get is x of t, the in-phase component gets modulated by a cosine function, and the quadrature component gets multiplied by minus sine 2 pi fc of t. So how does a transmitter structure look like? Well, so how does the TX look like? It will look like this. So first of all, you have your M of T. This guy, okay, maps to baseband signal, right? So now what you got is X of T and Y of T. Now, what we need to do is multiply these two fellas, okay? And this is how you do it. So here, okay, you multiply by cosine 2 pi. Let me do it even better than that. So there's some local oscillator, LO. Okay, and this creates a cosine wave of a very specific frequency. Okay, now, okay, what do we do about this thing here? Because that's a sine. Well, that's very easy. You put a 90 degrees phase shifter, or minus 90. Minus 90. I might be wrong, but the reason is I need to get minus sine 2 pi fc of t. So same frequency, but it's sine, so it's 90 degrees out of phase. What this should produce at the end of the day, boop, boop, is a modulated in-phase component and a modulated quadrature component. Okay, and this and that get summed together, and that creates your passband signal here, PB. So, okay, so we saw the receiver structure there. Equivalently, if we go the other way, and we do magnitude phase representation, slightly different. Common base, we combine them together. E to the j 2 pi fc of t plus that fella. Okay. Now, okay, now how do we do this real thingy again? Again, Euler comes to save the day. That's the magnitude, sorry, not real operator. That should be cosine plus a phase term plus the magnitude, sorry, j sine okay. Real operator keeps this, ignores that. So what do we get? Okay. So this also is kind of interesting. So let's look at this a little bit more carefully. So what does my receiver structure look like here? So what we get is the following. So let's say here's your modulated signal. Sorry, your message signal. My bad. And now what it does is this is my mapping again, right? Mapping to G of m of t, right? So that's my G thing. Boop, boop. Now, this fella, la, 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 la. This one here is R of t. Okay, that's cool. That's not too bad, right? It's now the other thing. So here it produces that. Okay, so there's some sort of phase term I need to account for. So I have an oscillator, right? And what I need to do, so that oscillator, okay, 2 pi fc of t. So that's great. But what I need is a phase modulator here. And that's going to create 2 pi fc of t plus theta t. That now, folks, produces v of t. Okay, so that's the other receiver structure. Sorry, transmitter structure. Mu. So this is transmitter structure, TX structure, okay, where we have an in-phase and quadrature representation. This here is a transmit structure where we have a magnitude, mag phase representation. Okay. Okay, awesome. Oops. So now let's take this one step further. So we got this. So let's go. So we saw how that looks like. We saw how that looks like. So now receiver. So I mentioned this thing, the LO, the local oscillator, right? And local oscillators are actually critically important for a number of reasons, because that is what allows you to go to passband, right? It is supposed to be some sort of disciplined source of oscillation on which your carrier frequency is based off of, right? Like that FC is a frequency value. A frequency value of what? Well, it's driven by your local oscillator on your radio. Now, this is also a source of problems because when you wonder about the frequency offset, in many ways, that's coming from things like your local oscillator, because local oscillators are not perfect. Again, that's a topic for the follow-on course here with respect to 4305. So what you got to do is you need to have good local oscillators. Now, the problem is the higher the frequency of the local oscillator, they're more expensive. They're more prone to drift, right? They're causing the frequency offsets. So it's like there's this trade-off. You want to go to higher frequencies, but you're going to need a really good local oscillator. So there's some tricks that you can pull, okay, in terms of creating a local oscillator that's capable of transmitting, as well as what we're going to be seeing here, receiving signals. And what we're going to be looking at specifically is this thing called the super heterodyne receiver. Okay. Oh, and what the super het looks like is the following. You take a radio frequency. This is at passband frequency, your signal. What you do is you bring it down, but not all the way down to baseband. You move it down to something, an LO, right? Using an LO, local oscillator. And you bring it down to something called not your baseband, but to something called an intermediate frequency. Okay, so it's not passband, it's not baseband, it's somewhere in between. Then what you do is you filter out everything except the desired signal, and then you use another local oscillator and you bring it down another step. Okay, so like I think the best way to do this is to illustrate. So let's say you have this crazy awesome, so let's say the ideal world, ideal. Okay, means money is no object. Your local oscillators are completely awesome. And you don't have to worry about drift or any of those imperfections. So let's look at the frequency domain. Right? Here's 0 hertz. Here's minus FC. Here's plus FC. And suppose that you have a signal here and a signal here. This is in the frequency domain. How do you bring that waveform to DC? Right? So these are passband, and this is baseband. This is where you want to play. This is where you do your detection. This is where you do your signal processing. This is where you decode your signal. So to me, what you do is you demodulate. How do you demodulate? Well, let's go back. Well, we modulate using a cosine. Same thing here, cosine, and if we're 90 degrees out of phase, sine. So to me, I want to take whatever my passband signal is, let's say that's V of t, and to me, to demodulate, I would need to multiply by cosine with the exact same frequency, right? Because what is this when I translate it into the frequency domain? It's going to be V of f convolved with whatever the Fourier transform is of this fella. You know what that is? Ha! Delta f minus fc plus delta f plus fc. So this is great. What's another way of looking at that? So if that's my spectrum, convolved with deltas also located at minus fc and fc, what do we get? So the way I would do this, okay? Like whenever you deal with something like this. So this is the demodulation. So the ideal demod process. Okay. The way you would do this, boop, 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 boop. And then here's 0. Is you would literally treat this as that block, and you would convolve against each of the deltas. What happens when you convolve against a delta that's shifted, okay, and this time in frequency to minus fc and to plus fc? You get a copy of this thing shifted to centered at minus fc. So now 0 is now centered to minus fc. And you take another copy of this and you shift it to centered to plus fc. So the result is going to look like this. So one copy that's now centered at plus fc has a triangle located at 0. And we have another triangle, the double frequency term, at 2fc. Likewise, the other copy, there's going to be a triangle at minus 2fc. This is where my entire thing that I modulated to is going to be centered at minus fc. And another copy located at 0. Okay, great. Cool beans. Then what do? I filter. So I low pass filter. I keep whatever is at 0 and reject the double frequency term. And so at the end of the day, what I get is this. Ha! That's it. That's my baseband signal. And I'm a happy professor. But what would, so let's say I have, like, my FC is at 10 gigahertz. Well, I'm going to have a local oscillator at 10 gigahertz. or it has to generate an FC at 10 gigahertz. That's a big, tall order. So what's the trickaroo that I would do? Oh, boy. So the trick use the superhet. So the super heterodyne receiver, what the trick that I use is that I would actually use multiple local oscillators. Okay. And I would progressively bring the signal down, 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 down in small bits. So this is how I would do it. Okay. So this is the superhet approach. Okay. And the goal, keep FC small. Very important. So the way to do that here, okay, so minus FC, FC, 0 is the following. So what I would first do, and again, I would treat this as a block, is instead of modulating this thing with mu, with FC, sorry, with FC, let's say we choose FB. No, sorry, no. Ha. Let us try. I have a good acronym. See, this is what happens when you're thinking on the fly. So use FIF1, intermediate frequency 1. And this is much less than FC. Okay. Absolute value of FC. Nah, because I don't think we use, like, okay. So what ends up happening is, suppose I do that. The way this would work is essentially I'm moving the center to wherever IF1 is centered, right? So what I would do is, let's say this fella here is, bad, VF. Okay, so now what I'm doing is, okay, VF cosine 2 pi FIF1 of t. The result is this. So I would have that initial block, and now I take one block, and it gets moved. Let's say to here, FIF1, okay? And let's see, got to be careful here. Got to be super careful. I take another block. Yeah, that's it. And it goes to minus FIF we go. Minus FIF1. Okay, so let's draw it out. Boop, 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 and boop. Okay, great. So let's call this, okay, like a lower image, LI, higher image, HI. Okay. I mean, I'm just making this up because just to highlight. So now what we got is, now we got lower image, lower higher image. This is higher image. And this is higher lower image. Okay. So that's a little bit of a trick. Okay. So if we do this modulation, okay, what have I just done? Well, so now if you do the mathematics or just keeping track of the frequency, so the carrier frequencies are now, this here is going to be minus FC minus, okay, this here. So I'm starting with the easier ones. Okay, now this is going to be yeah. So this is going to be plus, yes, that's correct. Plus, minus, yeah. And this is going to be minus FC plus FIF1. Then what you would do is you would either low pass or high pass filter out the replicas and reject the others. Sorry, band pass. So what I would do, okay, is I would in this case be sneaky and just have a low pass filter that would cut off here and here. So this would be F low pass filter cut off. And this would be, sorry, and that would be minus, and that would be plus low pass filter cut off, right? So now we're getting closer. We've just, so what happens is it's not zero, but we've moved this progressively from where it was initially minus FC and plus FC. We've moved these copies such that now, okay, such that now it's FIF1 closer to DC. All right. So now what you could imagine, so these are rejected. Everything outside a low pass filter is rejected. So now I got this. I could do the same trick with, let's say, FIF2, FIF3, FIF4. I could keep on doing this all day until I get them all onto zero, or a low enough frequency that I can work off of a very low frequency passband signal. And there are receivers that can do that too. Okay. So progressively, what you can have, if we go step by step, is something that looks like this. Okay, so let's say this is your passband signal. What I can do is, as I go and move to, let's say, IF1, right? And then what happens is, again, I do this. So that's, I apply an LO, I apply another LO. Now I'm at IF2, or not IF2, but I'm moving, I'm progressively moving until I'm at BB, right? So it's a combination of local oscillator and low pass filter. So local oscillator, LPF. LPF or bandpass filter. So some sort of filtering until I get to where I want to be. So all I need is local oscillators with lower frequency than, let's say, FC, and I progressively do, demodulation, filter, demodulation, filter, demodulation, filter. Okay. And so even though the receiver chain is more complex, it's not a one-shot deal, the components are cheaper. So that's the trade-off here, okay, is components are cheaper. Okay, so lower frequency, lower freak LOs, but, so that's a pro. Con, more complex design. Okay, so folks, that is lecture 14. So you might say, okay, that's really cool. What would, like, let's say, a class test look like for something like this? Well, what a class test would look like here is I could give you a bunch of LO values, a bunch of filters, and I'll say, here's a passband signal, bring it down to LO, you got 20 minutes. Fair enough. I mean, so that's something. And then likewise for the transmitter structures, I could give you a bunch of components, and I can ask, build an IQ transmitter structure. Okay, so that would be something. That I would could easily ask in a class test environment. All right. So with that, that concludes lecture 14 of ECE 3311.